Hello everyone, it is June 28th, 2023, and this is the biweekly libhal meeting. Alright, so a couple of highlights, or like basically the agenda for today. I'm gonna talk about how we removed the HAL socket interface and why, the large refactor of the libhal ESP8266, introducing libhal-cmake-util, and finally on using vendor SDKs for libhal. Now, this is a short and sweet one. Socket was quickly put together and had some issues. I had some feelings about how I put it together, and it felt weird having that interface in there the entire time. I felt like I didn't think it through too much. I felt like I pretty much just put in an API that I would end up deprecating pretty soon. So I decided, since we're going to move to libhal 2.0 anyway, because we're going to take out the libhal tweaks file, I thought, you know what, it's a good time to take out HAL socket as well. So this is actually something I did along with that change. I just haven't talked about it yet. It kind of became more relevant because libhal ESP8266 was using the socket interface. Now, the refactor of the ESP8266 driver, which for the few people who don't know what that might be, it's just the Wi-Fi driver. The previous driver for the ESP8266 was complex and utilized a ton of RAII, resource acquisition is initialization, in order to help protect users from doing anything wrong. The idea was you create one object, then from that object create another object, and that socket that you generate from that other object, basically, it would close when it died. The problem is that you may want to close and reopen a socket whenever you need to. So it was kind of just bad design, and you had to basically kill the object in order to destruct the object in order to get that to work. And it was just, when I saw what code was required to make it work, it made me realize that this was a flawed implementation, and it was confusing people. So we have a new implementation, which is basically just a single class with a whole bunch of different APIs to connect, configure, and inspect your Wi-Fi and server connections. It only supports a single TCP UDP connection. The previous one was the same way. Nothing really changed there, but yeah, we only get one little socket to communicate. I'm gonna give you a little live tour of what that looks like. I think I can actually just show you from here. So let's actually close this on up. Let's close everything here. And then we can go over to ESP, go to include, AT, and we can look at some of the stuff here. So I'm just gonna move this guy back. I'm gonna zoom him in. All right, so the new AT class. Oh, snap. There's a socket. There's a random socket class that's not being used anywhere. I gotta get rid of that. The API is pretty simple. You have a create factory function, reset function, connect to AP, set IP address. Are you connected? Disconnect from the AP. You also have connect to server. Are you connected to the server? Write to the server, read server, and disconnect from the server. These all work as you might expect. You can connect to an access point, and then you can change your IP address, and then you can check to see if you're still connected. If you're concerned that you might not be connected, you can also connect to a server. You supply it with a socket config object, which specifies what socket type you're using, what the domain name is, or what the domain is, and then also the port that you want to communicate on. And yeah, that's pretty much that. In the implementations, the actual data stored is pretty small. This is only around about 24 bytes, probably padded out to be 4 bytes, 32 bits. We have another 32 bits for an array. So this guy is basically 2 pointers, the size of 2 pointers. A lot of the work is done during the run time of each one of these API calls to figure out if, to communicate and send commands and that kind of thing. So yeah, that's pretty much the AT command, the AT library. There is a demo that we have here. We have a couple. We have a very dumb, easy, pretty simple demo. We basically create the object here, connect to an access point, check if we're connected, print out that we're connected, connect to a server, example.com, send a GET request this is printing out. Send a GET request out to it. This needs to be bytes. Delay for some amount of time, and then read the stuff back. And we delay for a second, and this pretty much works. It keeps working. It works pretty well. And then if we go to benchmark, this thing's way more intense. But all to say that this actually will repeatedly send GET requests to a server, to one part to see, if the server will respond quickly, but also to see if our system can handle it. And our system can handle it just fine. It really turns into whether or not the server can handle the amount of pings we're doing. So yeah, that's what the benchmark is. You recommend that you use this mostly for your own local tests, not doing this against servers that like people actually need. So yeah, that's pretty much a large refactor of libhal ESP8266. You can look at the demos to get an idea of how to use them. Actually, one last thing to say is that the benchmark here does a lot of extra work. For the robotics team, if they're interested in using this thing, actually they're probably going to be using this. A lot of the stuff here they can pretty much reuse because it is built here to kind of show how do you reconnect, how do you reestablish connection and all that. So yeah, that's ESP8266. The next item is libhal-cmake-util. It basically replaces the CMake ARM embedded. Most people probably didn't ever work with this. They probably just saw that their libhal device template or the libhal platform template or their app already came with it, and they just kind of left it there. But basically what this thing does is it provides you a whole bunch of macro and helper functions and toolchain files to modify the way that CMake works, and also provide functions so that CMake can do some post-build stuff. Basically, there's no reason to call it ARM embedded because the CMake stuff is actually pretty much works anywhere. So it's not important for it to be called ARM by any means. And even embedded may not even make that much sense. So I'll give you a little live tour of what that looks like. Actually, I can click on this link here because I want to see... I want you guys to see the README. Let's go here. So the way that you include it is that inside your Conan file, you define build requirements, and you just put in tools required, CMake-util 1.0, until the number of this thing gets higher. Now, the thing about this is that in order to allow for customization, let's say you don't want to have the build output functions put into your code, into your project. Maybe because it conflicts with something else that you're doing. Maybe you're using some alternative to our CMake utilities. Maybe you don't want to increase the the amount of stuff that the CMake has to do. You want to decrease that to speed up build time. So that might be something you disable. But by default, it provides a way to generate a hex file, a binary file, disassemble the file into assembly, disassemble it with source code integration if you have debug information enabled, which we'll talk about that in a sec. Print the size information of the L file, and then also do a full build, which does all these steps, and then a post build, which is in contrast to the full post build, just only does a couple things, which is generate hex, generate binary, and then print out the size. The disassembly part can take a long time depending on how big the binary is. So yeah, that's what you get when you use this. And an example of using this would be, I don't know if I've changed it here. Yeah. So like libhal post build, and I take my executable, I pass my executable into this, and that will generate the at.elf file, and then the elf.bin file, and the elf.hex file, and same thing with the benchmark, so you can load these up onto your machine. If you don't do this, you only get the elf file, and you cannot flash that onto your device. And then next up after that, we have optimize debug build. This is a toolchain file that basically is injected into your code. It doesn't give you any functions to call. It just, once you say true, it will automatically be injected into your Conan toolchain.cmake file. What this does is, let me show you. Yeah, so it says optimize debug build. The idea is that normally when you use debug for, you do a debug build to, the whole point of doing a debug build is that you want to actually be able to debug it, either step through the code, and a lot of times, well, actually, I'll give a couple things about this actually. Debug builds can be used for a lot of different things. One of them is for unit tests, because you don't want aspects of unit tests to be optimized away. That's a problem. Another one is if you want to just inspect how a particular function would traverse ignoring optimizations being included, just to see, how deep a stack, how deep a call stack ends up becoming in certain functions. and that could explain why a performance loss is somewhere. Another reason would be you do want to just like step through your code and debug it and go through a debugger line by line and check everything. The thing is, if you use optimization level 0 for this, it ends up making your binary massive. Does very little optimizations, pretty much none of them. It's the whole point is turning it off. And you get the ability to step through your code, but not gonna lie, I've done this and it ends up feeling like too much stuff is available. A lot of stuff should probably be optimized away and it still be intelligible what's happening in your code. So that's why we're using optimization OG, which is very close to O1. OG is optimization for debugability. It turns on optimizations in order to reduce the code size, but also includes, but doesn't over-optimize to the point where you couldn't step through the code very easily. I think it also enables certain features that make debugging even easier. So it's a really good, it's the best option we have for embedded. We get a lot of optimization, not all of it, but we get quite a bit of it, which means better performance if you're debugging stuff in your debuggers fast enough, better performance, as well as also smaller binary sizes so you can actually load them. Another problem with debug, your binary sizes get so big that you can't even fit them into your device. So like it's not very helpful. So that's what this does. If you set this particular flag to true, it will automatically inject these lines into your build system and replace the original C flags and C++ flags for debug with OG and -G. -G just says incorporate debug information into the executable, which would make the L file bigger, but luckily for us, it has no effect on the final binary, so all that stuff gets stripped out. So it's almost always necessary or useful for us to incorporate debug information. The only time you want to disable this is when you're writing something proprietary. You want to keep all the debug information out so that people can't disassemble your project or your library. So yeah, so that's that. And then lastly, I want to go over the idea of using vendor SDKs for libhal. Now, when I was working on the pre-built stuff, I realized, well, a lot of the stuff that I've used in the past is open source, as I thought. It was open source. So, I mean, we could just use a lot of those libraries and hook them up to our interfaces. Now, the LPC library is written from scratch. So is the STM library. And most libraries that are written in SJC-Dev2 were all written from scratch. I didn't do this because I thought that, well, I did it because I wanted to optimize our stuff to our interfaces, but also because I want to give people a chance to write out the code. Now, expanding the ecosystem isn't as important. People learning is fantastic and huge, but having the ecosystem grow is also really important as well. Here's the rub though. Many of the vendor SDKs out there do not support us using them as a backend, nor us using them as inspiration. Now, the inspiration part's probably a little dubious. None of them really said anything about not using them as inspiration, but obviously, if you use them as inspiration and you end up plagiarizing their work, like copying and pasting it to some degree, that's a liability. So when I looked into it, I found that the NXP software license agreement and STM's license agreements are not allowable for what we want to do. And I can actually show you what it looks like inside of these. So if we go to distribution. All right, so so here's some of the license grant after you sign this license. Exclusively used with integrated with NXP products. NXP grants you the worldwide, personal, non-transferable, non-exclusive, non-sublicensable license under the NXP intellectual property rights to use the reproduced licensed software as part of or integration with within authorized systems on a standalone basis. So I read this as, I'm not a lawyer, but I read this as you can reproduce and do whatever you need for, so long as you're using it on our systems, but you can't just use it on your own. You can't just use it for something outside of what it's meant to be used for, what was meant to be built on. You cannot directly or indirectly demonstrate, copy, distribute, market, or sell the licensed software in object code, machine code, only as part of an embedded within an authorized system in object code form, not assigned on a low basis. So you basically, to some degree, I think this even says that I can't even like write drivers for someone and sell those, like using their code to write some solution for someone. I think that's what they're saying, but I'm not exactly sure. They do make a stipulation saying that the header files can be distributed in source and object form, and that's totally fine. But it seems to also be within, an authorized system, which I think might be relating back to their products. Copy used should be as needed solely in the connection with the authorized system. Maintaining, supporting, authorized, yeah. So basically, and I also like kind of just looked into more stuff to see what other people thought about this, and it seems very clear that we do not have control to redistribute this stuff ourselves, meaning that we can't put into our repo. We do not have the right to copy it as we do. So cloning, I don't be able to clone it, that kind of thing is not something we can do. If people wanted to then use our libraries, to then use this stuff for some, I don't know, some other chip. So actually, here's something that I'll bring up on the other side of this, is that like I found it really interesting, very clear in the STM documentation. I believe it says that it has to be on STM hardware. Yeah, so this software package, this software package or any part thereof, including modification and derivative works of the software package, must be used and executed solely and exclusively on or in combination with a microcontroller or microprocessor device manufactured by or for ST Microelectronics. They make it very clear the software is not meant to be loaded on anything else. And I was trying to think to myself, well, why? Like, what's the problem here? Because the first thing I thought of was like, wait, hold on. Does that mean I can't run host tests on your code? Like, I can't like take the code and write some unit tests that intercept its read and write operations to certain structures or what would be its own addresses, and then like doing work with that. That seems kind of weird. Can I put it inside a VM and just emulate this thing? Turns out the answer is pretty much no. You can't, as far as I can tell. I might be a little pedantic, but for the most part, I don't think anyone's going to care. But like, they pretty much make it very clear this software is meant to be only run on our devices, and that's it. And it took me some time to realize what the real reason for this was. And that's because they have a competitor, the GV32F. GV32F 103. So a lot of the libraries that are, this chip right here. A lot of the libraries that work on the STM work on this thing. And this one's actually, I think, an ARM chip. They basically just copied majority of like the libraries from, well, not copied. They copied all the peripherals and how they operated onto this chip to make it look almost identical to an STM chip. Its naming and numbering scheme also matches exactly the same STM chips that's supposed to be used for. And a lot of the libraries could be reused on this chip as well, maybe with a slight modification. They make it very clear that you're not allowed to do that. So this is basically me saying that and making it clear to everyone here that we are basically not allowed to use any software development kits for any libhal software. They have some stipulations about like how you can't open source these things because then it would change their licensing in some way. It would go against the licensing. So yeah, NXP is no game. STM is not a thing. But ESP-IDF is Apache 2. So technically we could do whatever we want with that software. So that is one where we could totally just look at the source code, come up with look at how it's done, and then just go implement that. So I guess the two things are, number one, we cannot use these as backends, just period. We have to make sure we do our due diligence to look at the licenses and see what they require. And I'm not going to say that we shouldn't look at them for inspiration, but more that we should definitely take a look at their licenses before we consider those options. And I feel that it's in our best interest to just simply not look at their code, look at their data sheets, and write the code from there. And yeah, that's pretty much the idea. And that's pretty much it for today's meeting.